take a look at it. We'll see what it's asking us and stuff, and we'll decide if we want to go further from here. I should mention there are going to be a lot of ways to solve this one, so I don't think there's any possible way we could go through like all of the solutions that are possible here, but we'll take a look at a few. Okay, imagine a white rectangular grid of n rows and m columns divided into two parts by a diagonal line running from the upper left to the lower right corner. Now, let's paint the grid in two colors according to the following rules. A cell is painted black if it has at least one point in common with the diagonal. Otherwise, a cell is painted white. Okay, cool. So, something I want to make kind of like a little clearer about this one is the strict conditions under which it should be painted black. And okay, actually, this is a good example. This sort of shows us. So, okay, first of all, I might have forgot to mention we want to count the number of cells that are going to be painted black here. So that's the challenge. We're given the dimensions. We're given n and m. So like in this case, let's say it's 3 and 4, and we're dividing this line across the diagonal. This is a really cool problem, actually. It's really mathy. I think that sort of accounts for why there are so many different kinds of solutions here. But anyway, let's move on for now. So in this case, if we go across, we sort of notice like, okay, the line goes through this cell, goes through this one, this one, this one, this one, this one. So we have 6 in total. So we'd say the answer is 6. Now in this case, kind of surprisingly, we have a smaller like field here, a smaller rectangle that we're dealing with. And before anyone says anything, a square is a type of it's a type of rectangle, okay? I've heard debates about this. I've had a lot of students try to challenge me on it. It's a rectangle. Anyway, so this rectangle is smaller than the previous one, so that might be a little surprising that it actually has more of these black squares in it. But this reveals a really important fact about this problem here, about the way they're asking it. And it's that each square includes its edge. It includes its border. Okay, so that's really, really important because the borders are like shared. But each square includes them. Each cell includes its own border. So like this corner right here, this vertex, it's shared by all 4 of these squares. So for the line to go through that means instantly all 4 of these guys are going to be lit up. So that's at least part of the reason why in this case we actually have more of these shaded cells than we would in this larger rectangle over here. Because if they didn't have a shared border, if they didn't include their border, then it would basically just be the main diagonal. We would just have 3 in this case. So that makes a big difference. That's like more than double. Okay, cool. So how are we going to do this? Good question. I mean, something you might notice right off the bat is these can be pretty big. So let's see what we can do. I actually want to take a bit of a detour here before we go any further. I want to go to desmos.com/calculator. We've used this before, but in case anyone hasn't seen it, this is a really great free app. It's browser-based and it allows you to graph stuff. So we could do something like, I don't know, let's look at rational functions today. We haven't done something like this before, I don't think. So let's say we've got like ax cubed plus bx squared plus cx plus d, and it's being divided by px cubed plus qx squared plus rx plus s. Yeah, okay. So what are all these things? What's A, B, C, D, P, Q, R, and S? Well, let's just put sliders on each of them and let's get them going. Just each doing their own thing. And whoops. Oh, what's going on with these? Can I not animate that one? R. R is, I can't use R. Yeah, R, let's use T. So I can't use R because R is for like radius, I guess. So it's kind of a, what do you call it? Like a keyword sort of, like it's like set in stone. It's like a constant. Yeah. All right, so just changing up the speeds of some of these guys so they all animate a little bit differently. That can be one. Let's make these guys a little slower. There we go. And yeah, that's our graph over there. And maybe we can change this if we want to change the color, for example. Let's make it green. And let's go on projector mode so it's a little thicker. Yeah, okay, that's good. I like what I'm seeing. So this is like, I guess, you know, these are the kinds of functions you might have to sketch in like a pre-calc kind of class usually. Around these parts in Ontario, we call it advanced functions in grade 12. But anyway, pretty cool. So this is the kind of stuff that Desmos can do. It's also really good. We've used it for like regression and that kind of stuff. And it's, yeah, really useful for those kinds of things. Let's clear that out. So, all right, why did I bring this up? Well, basically what we're talking about over here is linear relations, right? Now, what I actually want to do for our rectangle, and let's maybe draw our rectangle. Could we do something like this? Let's say, maybe let's take like an x thing and restrict it. So, okay, let's do a double inequality where we say 0 is less than x, which is less than whatever our x boundary is going to be. So, what are they called? M and n? I don't remember which is which. I don't think it matters. Well, actually, let's just be consistent with this one. So in this case, m was 4. So yeah, this is the x is m. Great. And we'll set it to 4. Okay, but we want to restrict this. Oh, geez. How do we do that again? We want to restrict it. It's like this. Is it like this that we restrict it? Or no, we would do the y's. Okay. I'm all mixed up here. And this one was 3. Great, so we'd do the y's, I think, and then we'd restrict it, so we'd do something like this. Yeah, that's good, right? And then do we need to show the border? Can we make it not dashed? Is that a possibility, maybe? That must be a possibility, right? For it to not be dashed? Maybe it's not a possibility. Okay. Well, I guess it would become solid if we made it like equal, and technically it should be equal. So let's do that. Okay, so that gives us our rectangle, sort of. Sorry that took so long. Let's change the boundaries on these. Let's make this go from 0 to 10, and the step is going to be 1. Same thing with this one for now. Step of 1. Cool, so now we can sort of change the playing field that we're looking at here. I'm pretty sure there's a way to get rid of the actual lines on this thing, but, you know, who cares? Actually, maybe it's as simple as just switching these. Would that work if we did this? No, I guess not. Same sort of issue, just in different dimensions. Okay, well, you know, that's fine. We're not going to worry too much about that. So what do we have? We had 4 and 3? Yeah, we had 4 and 3. Cool. And now we want to do something with this. Oh boy, we're calling these m and n. Well, that's too bad. I was going to use m for slope, but no, you know what? That's probably fine because we'll use standard form. Okay, so we'll use s for slope for now, and basically it's just going to be rise over run, right? So if we're rising this many, so that's 3, this is 4. It's basically just n and m, right? So it's going to be n over m, n divided by m. Okay, so that's s for slope, and we're going to say y equals. Wait, hold on a sec. So. Actually, okay, just out of habit, I'm going to call this P mainly because I have a bit of an allergy to using like letters like S or O or L because they look like 5s or 0s or 1s. So let's go with P for now. It's at least right for the French word. Anyway, the point is we'd have like y equals mx plus b normally. We'll say px plus b, but b in this case is just going to be 0 because we need for it to go through here. So it's just going to be y equals px pretty much. Yeah, notice it's going through both this part and this part. Let's even restrict that maybe. Let's say like where x is going to be less than or equal to m. Yeah, so we're just looking at this part of it. And we want to know which ones are like making contact with this. Okay, so let's see. There's one change I want to make to this. This is in like, you know, y equals mx plus b form. I want to put it into a different form. I want to put it into standard form. So basically what I mean by that is standard form is where we have like ax plus by plus plus c, big C, equals 0. So in this case, what are we going to use for A, B, and C? Well, first of all, C is going to be 0, so I guess we can just totally forget about it. For this case, I guess B is going to be -1. We're just going to subtract y from both sides, and we're just going to have px here. So let's just even call this capital A just to make this a little bit easier. And we'll put the A on that one as well. So there we go. So I've plotted this line here. Ax minus y is equal to 0. And I might as well make that a different color so that it kind of, yeah, okay, cool. So that's our line. And we sort of want to know, like, if we were given like a set of x and y values, we would want to know if they lie on this line, right? So we could do something like this. Let's put in a table, and we're going to make a function here. It's going to be a function that takes in x and y, and it's just going to return ax minus y. Yeah. And so let's take a point here, like let's say the point, I don't know, 2, 2, right up here. Okay, 2, 2. And let's put in another series here, is that what you call it? There we go. F at x1, y1, because this is x1 over here, this is y1 over here, so this is f at x1, y1, where f is this function down here, so it's going to give us a times x minus y. But, you know, I'm not actually that interested in it. Now, I'm not getting 0, which means it's not lying on the line, and that checks out. It checks out. It's not lying on the line, so that's good. It's consistent so far. What if I gave it something like 3, 1? Okay, now it's a positive number, but it's not 0, so I guess that makes sense. It's not on the line. All right, let's try something that we know is on the line. Let's go with 0, 0. That's definitely on the line. And there we go. We're getting 0 for that one. Even if we went with like 4, 3, whoops, I meant to put a 4 in there, we get a 0. Cool. So we get a 0 for stuff that's on the line. We get not 0 for stuff that's not on the line. But I want to be a little more specific about this because we're getting negative over here and we're getting a positive over here. When do we get a positive and when do we get a negative? So let's try like 1, 3, negative. Okay, and notice just like the 2, 2, that's like above the line. I don't know if that's a coincidence or not, but let's take one that's below the line over here. So maybe let's try like 2, 0. Okay, that is positive. I would say our case is getting pretty strong here. So here's what I'm going to do. Instead of plotting ax minus y equals 0, let's plot ax minus y is less than 0. And take a look at that. So it is the dividing line. If you're above the line, you're negative. If you're below the line, you're positive. If you're on the line, you're 0. 0 cool. Anyway, the point is, these are all going to be sort of important facts about what we're going to do over here, because I realize the line's not going in the same direction, but this is basically the same thing that we're looking at over here, right? So I think we can probably use this knowledge. We're going to have this a value that's going to be n divided by m. We're going to have this this formula here, this f at xy formula, that's going to be ax minus y. So in other words, n divided by m times x minus y. So let's do that. Let's start with that. So we'll just say function f, and it's going to take x and y, and it's just going to return m divided by n. Was it m divided by n or n divided by m? It was n divided by m. Yeah, rise over run. Rise over run. I don't think it's going to make that much of a difference in this problem for symmetry reasons, but might as well just be consistent with what we were doing in Desmos, right? Okay, cool. So is that good? Is that what we had over here? Let's just sort of verify it. We'll put it all together in here. N divided by m. Yeah, same thing. It's good. It works. Everybody's happy. Awesome. So we're going back to this. Now, why did I do that? Why did I bother with any of that stuff? Well, let me tell you. Check it out. Can I just delete these? Can I like just go through and delete these? Yeah. Now we're talking. Okay, so what I want to do is, actually these two are fun. Let's take a look at this square in particular, okay? And then we're going to compare it to maybe its neighbor. And, oh, see you later, Rainbow. Thanks for stopping by, man. Okay, so we're going to take a look at this square. We're going to compare it to one of its neighbors. So the vertices of this square, we've got 2, 2, we've got 3, 1, we've got 3, 2 as well. So let's put that in. And we've got 2, 1 as well. Okay, cool. So something to notice about these 4 values is that not all 4 of them have the same sign. So 3 of them are positive, 1 of them is negative. Okay, maybe that's a coincidence, maybe not. Let's do another square. Let's just do a totally different one just so that we don't have any overlap over here. Let's do this one over here. So we're going to have 0, 3, 0, 4. Whoops, not 0, 4, 0, 2. My mistake. And then 1, 3, 1, 2. Yeah, okay, cool. And then we find for this one, all of these values are the same sign. And it does not have the line on it, so it would not be shaded. So basically my claim here is that any square that, if we were to look at all 4 of the vertices and check if they're all the same sign, if they're not all the same sign, then that there must, okay, if they're not all the same sign, let's just think about what that means. So first of all, let's ignore zeros for now. Let's just think about positives and negatives. So if one of them is negative and all the others are positive, that means 3 of those points are below the line and 1 of them is above the line. Well, that means definitely the line is going through it at some point. We could even bring in zeros and say, what if one of them is 0 and all the others are, I don't know, negative? Well, that means 3 of them are above the line and 1 of them is on the line. That would be the idea for that one. So basically what we're going to do for this is we're going to do kind of a brute force approach for our first try here. The way it's going to work is we're going to make, I don't know how we're going to do it exactly, if we're going to use an object or what kind of data structure we'll use, but we'll do something to represent each cell. Okay, we're going to go through each cell, and for each one, we're going to check each of the corners, and we're going to see if they would all have the same sign if we applied the f function to it. Okay, so that's basically the idea. In fact, you know what? We could probably make this a lot easier. Yeah, we could probably make this a lot easier if we did something like this. Instead of just returning that, if we did like the sign of that. So like, yeah, let's do something like this. And maybe we shouldn't just call it f. That's kind of, I don't know. We'll say let equation value result. Let's just call it result. Okay, let result be assigned the value of that, and we'll say if result, or should we do a ternary? Return result is greater than 0. If it's greater than 0, then we'll say positive. We'll just use the word positive because then we can just do like an equals equals comparison. It'll be easier in the long run. Okay, positive. Otherwise, is result less than 0? If it is, then it's negative. And guess what? If it's neither of those, it's 0. Okay, cool. So there we go. That looks good. So we just want to return that. So let's see. I want to test this. So we're going to do f of, well, I'm using this first example here. So like for test 1, the values we have in here should be consistent with what we have in here. So like, for example, if I were to put in 1, 3, I should expect a value like this to come out. Or actually not specifically that. It should just say negative, I think, right? Let's try that. 1, 3. Let's try running that. Yeah, negative. We're getting negative for the first test. Makes sense. We could even do like a console log of result. Run that and see specifically what it's telling us, what result we're getting here. And I think it was supposed to be negative 2.25 for that first one. So yeah, negative 2.25. Looks like this is working good. So our f function is working the way we want it, the way we specified it in here. We're going to use that on each of the 4 corners of each of our squares, and we're going to see if they're all the same. And if they are all the same, then it's not shaded. So I guess we only really need to know how many of them are shaded. So we'll just do like a plus plus. So let shaded be 0. And that's ultimately the thing that we're going to be returning at the end of this. Yeah. Okay, cool. So under what circumstances is a cell going to be shaded? And how are we even going to do these? So let's see. I guess we could do something where, okay, what was it again? Yeah, these numbers are pretty big, but they're not that big, right? Like, even if we were to multiply the biggest of these, right? Like 10 to the power 5 times 10 to the power 5, that's 10 to the power 10. That's huge, but it's not too huge, I don't think, right? Like if we were to do return, what is it? It's like number dot, like, is it max safe integer? Can we do that? Max safe integer? Yeah. See, that's huge, man. Like, okay, how big is that? We've got 3, whoa, it's a million, a billion. Yeah, okay, so like that's 10. That's 10 digits right there, right? That's 10 digits, I think. Technically 10 to the power 10 would be like 1 greater than that. But yeah, that's a small fraction of what our max safe integer is, so that's fine. We'll use hashes. Is that smart? I don't know. Do we even need to? No, I don't think we even need to for this, right? Like, we could just do a loop on this. Let's just do a loop on this. Yeah, that makes sense. Okay, sorry, I was overthinking it, I think. Let's say I is going to start at 0. I is going to be less than, which one is this? This is going to be the x or the y? The I will be for the x, let's say. So it's going to be less than m. Why less than m? Well, because this is going to represent sort of like, if we're looking at our diagram, it's going to represent like the upper left corner of our cell. So like this would be 0, 0. This one would be, what would be 3, 2? Yeah, 3, 2. And that would be the biggest one that we want, right? So we want it to be specifically less than m, and we're going to say that j is going to be specifically less than n. And we're going to do a plus plus on that thing. Now there's going to be some symmetry, but we're going to ignore that for now, and we're just going to brute force it, go through each one, and do our thing. What are we going to do with each one? Well, yeah, what are we going to do with each one? Okay, we're going to do this. So we're going to get all 4 corners. Get all 4 corners. Cool. Yeah. And then we want to determine if it's shaded. So how are we going to do that? Get all the 4 corners f values, I guess is what I mean. Like we're going to launch the f function that we had above, right? This thing. And we want to see if they're all the same. So get all of their f corner values. Check if they're all the same. Yeah, okay. We'll do that. Cool. All right, and then how should we do this? We'll say const corners is assign the value of just this empty array. We want to get all their f values. So we'll do something like, I guess another little nested loop here. We'll say dx. Oh, you know what? Instead of I and j, why don't we actually just use x and y? I think that makes more sense. Sorry, I'm very indecisive about this one today. Oh well. Okay, so dx is going to be 0. Yeah, it's going to start at 0. It's going to be less than or equal to 1, and we're going to plus plus it. And we're going to do the same thing with dy. This is probably overkill, like in many different ways. This is probably not the best way to do this, but it's the way I'm going to do it. So basically, I'm just doing this to get all 4 corners. Okay, so for our 4 corners, yeah, we'll just like push them one at a time. It's fine. It doesn't matter what order we go through them at. So just to sort of demonstrate this, let's say we had an x value and a y value. Well, hold on. I don't want to have to hold too much in our heads here. So let's just do a little table over here. So we've got x, We've got y. I guess rainbow sprinkles is gone, so I can make these nice and sloppy. So cool. Nice. There we go. So x, y, dx, dy. And let's say we're talking about this cell over here. I guess the butter popcorn color doesn't show up as well on this side, but oh well. Anyway, that's the square. So x and y. Oh, no, not that square. No. Let's do this one. For the sake of variety. Yeah. Okay, so this is going to be x value of 2, y value of 1. So that's 2, 1. And for dx, it's going to start at 0, and it's going to execute this loop, which is going to also start at 0. And then the dy is going to go on to 1 while dx is still 0. Then dx is going to move on to 1. dy is going to start at 0, and then we're going to have 1 and 1. So our x and y values, well, okay, I guess I'll write the actual x and y values here that we're going to end up using. So 0, 0, we're not modifying it. We start at 2, 1. It's going to be 2, 1. In this case, we're adding 1 to the y value, so we'll get 2, 2. We're adding 1 to the x value in this case, so we'll get 3, 2. We're adding 1 to both here, so we'll get 3, 2. The previous one should have been 3, 1. Oh, I was too impatient. Okay, great. So let's take a look at these. So 2, 1 would be over here. 2, 2 would be this one. 3, 1 would be this one. And 3, 2 would be this one. So those are the 4 corners that we're looking for. Okay, cool. So that's why I'm doing all these loops here. Now, I realize it might seem a little intimidating. It might seem a little foolish, actually, to do so many nested loops, especially since we know that the guarantee constraints are like so big. So I don't know. We might not pass all the hidden tests on this one. There won't be a guarantee of that, so just wanted to let you know. But we're going to have fun along the way, and that's going to be the main thing. Okay, cool. So let's just say corners.push f at x plus dx. Yeah, x plus dx, y plus dy. Because we know that all of those are going to be corners. So those are going to be valid corners. And we want to check if they're all the same. So we'll say if corners, I want to do this in a slick way. Can we do this in a slick way? Let's try this. Corners dot every, if corners dot every, okay, let's do it this way. If corners dot every, we'll put a function in here. It's going to take a corner, and it's going to say every one of them is going to be equal to corners at 0. I'm just using corners at 0 because it's one of them, but I could have just as easily used 1, 2, or 3. It just has to be one of them is the main point. Okay, so we got corners dot every, and we want to check if they're all the same. Is this going to check if they're all the same? It will. And actually, I shouldn't put a semicolon there. What am I doing? Anyway, but really what we want is if they're not all the same, we want to increment shaded. So I'm going to put the not in there, and we'll do shaded plus plus. Okay, cool. What's left to do? I don't know. Let's try running that. Let's see what's going on so far. Have we run this yet? I'm not sure. Okay, execution time limit exceeded. That's kind of what I was thinking. But take a look. Look at all these ones that it's passing. That's pretty good, right? That's pretty not bad. Yeah, I think that's pretty good. So, all right. I think this is like a good illustration in the sense that, okay, no surprise. These are pretty damn big, these numbers here. Those are huge, man. Now, wait a sec. 10 to the power 5. Oh, yeah, that'd be like 100,000. I was thinking 10,000. Yeah, these are really big. So I'm wondering just how bad it was, just how inefficient it was. Because we probably don't need to do all of these each time, right? Like in the sense that we've already seen these for the most part. We start over here, we go across. By the time we get to let's say this square, well, we've already looked at the one to its left. We've already looked at the one to its up. We've already looked at the one to its up left. So we have 3 out of the 4 points. We really should only have to really provide one more. So, unless it's like one of the ones on the edges. So, okay. I don't know if that's the issue, though. I have a feeling it's not the issue. So, let's even just take all this stuff. Let's take all this. Let's cut it out. Let's say do nothing. Let's try running that. And we're going to see if that even allows the test to be completed. No. So, see, doing a double nested loop on this, it's not going to work. And we're not even calling our function here. We're not even doing anything in the loop. It's just the very act of increasing all these. It's not working. Now, when I say like it's not working, what I mean is it's timing out. You know, it's exceeding the 4-second time limit that we're given for this problem. It would work in principle. It would just take a very long time. But it's kind of good that they're restricting us in terms of the time because, like, you know, again, let's say this was on a web app. Let's say this is on a game, right? Like, this is a game-like kind of thing. We wouldn't want it to have to, like, freeze and take forever or drop frames or lag or something like that. We don't want any of that stuff. So let's not have to worry about that. Let's just make an algorithm that's going to run in a more reasonable amount of time. Okay, so this is not that algorithm. It's not the one that we're looking for. So I don't think we could even modify this, like this idea. I don't think we could modify it in a way that would make it good. So that would make it work. So what are we going to do instead? Well, I have kind of a different idea, but I'm just not sure if we should do it now or later. I'm kind of thinking we might just wrap it up for now, and we'll just sort of resume this next time. How's that sound? Well, yeah. Basically, I'll tell you about the idea that I have, okay? So on something like this, there isn't really much of a difference between looking at the entire grid, you know, like checking every single point, versus just going along the line and just checking the ones that are affected, right? It's about the same amount of time, or it's about the same number. They're within the same ballpark. But if this got really, really huge, it would become less and less and less. Like the shaded region is going to become a smaller and smaller and smaller fraction of the entire thing. And so for that reason, it's going to make more sense if we fix our attention on the line itself instead of just the entire field. So next time we meet, we're going to resume this. We're not going to look at every single point. Instead, we're just going to look at the points that are affected by this line. So that's going to be the idea. Okay, cool. So we'll meet back here tomorrow. We'll continue with that one. And who knows, you know, maybe we'll complete that and we'll find that there's like even some other ones that we'll do next time. We'll have to wait and see. We'll have to find out tomorrow. As for now, thanks for watching. Remember to believe in yourself. Congratulations on destroying task 33, and have a great night. Bye.